Now we'll talk about a few different types of voltaic cells that you may have come across or heard about. And the one we're going to start off with is a traditional household battery. This is what's called an alkaline battery. In this reaction, zinc is being oxidized while manganese is being reduced according to the equation that's up on the screen. The battery is called alkaline because the zinc anode is placed in a hydroxide gel. Hydroxides are alkaline substances. Right now, there are a couple of differences between this and what we saw previously for our voltaic cell. First off is that the case provides both electrodes, right? So our anode, which is at the bottom of the battery, that flat section, it's the anode because that's in contact with the zinc. The cathode, which is the top section with a little bump at the top of the battery, is the cathode because it's in contact with our manganese. Now also notice we don't have the same type of salt bridge that we had before. This salt bridge is formed with a paper membrane that separates the two components. The paper is semi-porous. It allows ions and such to transfer through without allowing complete transfer. This is actually important because, fun fact, if the membrane is ever damaged in any way and the two half reactions are allowed to come into direct contact, the battery short circuits and that will produce a lot of heat. I'm not sure if you remember this, but there used to be a problem with the Samsung Galaxy Note phone, specifically the 7th edition, where the phone battery had a manufacturing flaw. Some of the battery cases were pressed so tightly together that it caused the paper membrane to rip, which means that as the phone was being used over and over again, the reaction was short circuiting and it caused the device to catch fire in your hand or in your pocket. Another application that you'll see, this is the subject of a lot of current research is being done, are fuel cells, right? So if anyone's ever seen a hydrogen fueled car, the way that it works, and this is a simplified version of it, is that hydrogen enters in the system and it comes into contact with the anode. Both electrodes in this case are graphite with a platinum catalyst embedded inside of it, right? So the hydrogen comes into the anode, it gets split into protons and electrons. The protons travel in through the acidic medium, the electrolyte solution, while the electrons travel through a wire and power everything electrical the car needs to operate. After it's gone through, everything winds up meeting back up again at the cathode. And when they meet back up, they also meet up with oxygen. And when you get the protons plus electrons plus oxygen gas, it forms water vapor, which is what comes out the back of the car as your exhaust. So your tailpipe just spews out drops of water. Another application of this type of redox reaction is what's called corrosion. Corrosion is simply the reaction of a metal that comes into contact with water, right? So in this case, we have a piece of iron. Some of that iron is submerged under a water drop. What's going to happen is that iron will little bit by little bit dissolve. The iron ions travel through the water to the edge of the water droplet, and the electrons will travel through the metal to the other edge of the water, or to the same edge of the water droplet. There, they're going to meet up with oxygen, and that will form some type of metallic oxide. As we can see from the diagram, the space underneath the water droplet, because it's acting like an anode, and anodes' masses get physically smaller as the reaction proceeds, the iron there gets eaten away and eaten away and eaten away, which goes to damage the structural stability of the component, right? So it might actually be useful for us to talk about a couple of ways that we can prevent corrosion from occurring, right? So two common ways to prevent corrosion. The first is just to completely cover it. Paint is one example, right? So if you paint over the surface of a metal, oxygen and water can't come into contact with it. Now, this doesn't work forever, unfortunately, right? If you leave paint exposed to the elements for long enough, the paint will eventually degrade. It will allow water and oxygen to come into contact and things will continue to corrode. This is one of the reasons why, for example, you've been seeing a lot of bridge work being done if you're driving on highways in the state of Massachusetts, right? There's so much water and salt and everything that gets dumped on roads in the winter that it damages the paint structure. So what you have to do is sand off all the old paint, get rid of whatever corrosion is there, and put a new coat of paint on it. And you have to do this every few years in order to prevent the bridge from rusting at whole, lest you get what happened on, I think it was I-80 in Minnesota, where the bridge was so corroded that it collapsed into the Mississippi River while people were on it. Right, so paint is one way. Another covering you can do is what's called galvanization. What you do here is you coat your substance with zinc, because zinc, when it undergoes corrosion, forms zinc hydroxide. And zinc hydroxide is very non-reactive, so it will protect whatever metal is lying underneath it. So if you go to the hardware store and you see galvanized nails, that's what those are. They're iron nails with zinc coating, right? But like we said, these don't work forever, especially if you're in some pretty tough environments, right? So the Navy, for example, naval vessels spend a lot of time in the ocean, obviously, and a lot of their hull is submerged. The salt combined with the water does a number on paint. So while the Navy does paint their vessels regularly, that's not enough. So what they do is they take plates of magnesium, giant like 2-ton plates of magnesium, and literally bolt them onto the hull, because what happens is that the magnesium is more reactive than the iron, which means that it will react before the iron reacts. Right? So our magnesium is going to oxidize, turn into magnesium ions, and the anode there will get smaller and smaller and smaller until it goes away, at which point the iron will start corroding. So what the Navy needs to make sure of is that each ship gets into port often enough to be able to change out this sacrificial anode prior to their causing severe damage to the ship. Right, so that's it for this video. In the next video, we're going to talk about electrolysis, which is using electricity to perform non-spontaneous reactions.